Hello, everybody. My name is Amy Oliver, and I'm so pleased to welcome you to the 51st annual New Vistas in Astronomy lecture series with the Fred Lawrence Whipple Observatory, part of the Center for Astrophysics, Harvard and Smithsonian. We're located out here in sunny Amado, Arizona today. I hope the weather is calm and comfortable for all of the rest of you. Although if you're joining us from the East Coast, I know it's a little chilly out there today. And so if you have not joined us before, you'll find that you may be joining us from any one of 3 different venues. You may be on Facebook, YouTube, or in our Zoom live with our speaker today. So we will ask you to go ahead and put your questions in the chat, and then we will feed questions live on camera to our speaker at the end of his presentation. And if you need anything else, you can also message me directly through any of these various channels, and I will help you with any tech problems that you're having along the way. Today, our MC is one of our education volunteers, Stephen Brown. So Stephen, go ahead and take it away and tell us what we're going to learn about today.
Okay, thank you, Amy, and welcome to everybody and happy St. Patrick's Day. Today, our guest is Dr. Wystan Benbow, Director of VERITAS, Very High Energetic Radiation Imaging Array System, located right at the Whipple Observatory. For those that have been to the Observatory Visitor Center, this array is made up of 4 large 12-meter telescopes located around the center. So it'll be very interesting to learn more about what's in our backyard. VERITAS is the most sensitive, very high energy observatory in the world. Dr. Benbow received his bachelor's degree in physics and astronomy from the University of Iowa. He completed his master's and PhD in physics at the University of California, Santa Cruz. His career has taken him from California to Germany at the Max Planck Institute for Nuclear Physics, and in 2007 he joined the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts. Dr. Benbow has been the director of and principal investigator and project scientist of VERITAS since 2008. He has written over 200 articles, published in journals, and made over 60 conference presentations and public lectures. Dr. Benbow was awarded the Smithsonian Astrophysics Observatory Award for Superior Accomplishment in 2016, 17, 18, and 19. Today, Dr. Benbow will discuss the history of gamma ray astronomy at the Whipple Observatory and highlight some key results from VERITAS and summarize the status and future of this new cutting edge field of astronomy. Doctor, thank you for taking the time to share with us today what's happening right in our backyard in southern Arizona at the Whipple Observatory, and you can take control.
All right. Thank you, Stephen. As you mentioned, I'll be discussing pretty much the history of gamma ray astronomy and how it was pioneered over the past 50 years at the Whipple Observatory. And it's very interesting that I get a chance to speak today on St. Patrick's Day because it has very much an Irish history to the field. It very much started in Ireland, and a lot of the major characters in its early history were Irish scientists. So it's a delight to be able to speak today on this matter. So I am a director of VERITAS, and you see the array down there as it exists at the Whipple Observatory right now. But I'm going to jump back in time and mention a bit about VERITAS and how it operates. As soon as I can get the slide to advance. Okay, but I want to start out before I get going on gamma ray astronomy and explain a little bit to give you a foundation of how this telescope operates. And so what does VERITAS do? Well, it does TeV gamma ray astronomy, or Tera-electron volt gamma ray astronomy. So we look at gamma rays from the sky from about 1/10 of a TeV to 30 TeVs. And most people, if I think about gamma rays, the first thing that comes to mind to me was Bruce Banner being converted into the Incredible Hulk by gamma rays. So they seem like these exotic things. But really all a gamma ray is the highest energy form of light. And so light itself carries energy. Optical light, the stuff we see with our own eyes, carries an energy of 1 electron volt. And I'm going to convert that shorthand to volt just to be simple. Okay, and blue light, which you can break light into a spectrum, blue light has more energy than red light, and gamma rays have a lot more energy than optical light. And so a TeV is a trillion volts or a trillion electron volts, and that's a million. So, I mean, that's a lot of energy. And so if you want to think about what creates a TeV, let's think about thermal radiation first. I mean, we all think about stars in our sky, and those are thermal radiation. What is thermal radiation? Well, hot objects glow, and I think we know that hotter objects are bluer. And you can see down in the corner of this plot, there's something called black body radiation. It's a pretty well understood process, and the hotter something gets, the shorter of a wavelength, or the bluer, if you will, the energy of which it peaks. And the hottest objects in the universe are about 10 billion degrees Celsius. Okay, and those give off, photons at a peak at about 1,000 electron volts, or in the X-ray band. So VERITAS is studying at a trillion volts, and these are gamma rays. What's going on? Is this place, truly hotter than hell, if you will, or something else? And well, the secret to all of this is that TeV radiation, or trillion volt radiation, is non-thermal. So, and really anything above 1,000 volts is non-thermal, and this radiation is produced by particle accelerators. And so you can see man's best particle accelerator down here in the lower corner. It's at CERN, it's the LHC, and you can produce 10 trillion volt particles at this accelerator. Okay, that sounds pretty impressive. It's about 6 miles across, lots of magnets, and amazing technology to build this, the best thing we've ever made. The problem is that producing a trillion volt light, you actually need particles accelerated to more than 100 trillion volts, so bigger and badder than anything you've done on Earth. Okay, and so what we're studying with VERITAS is nature's most powerful particle accelerators, and one example is up here in the upper left-hand corner. Okay, this is something called an active galaxy, and I'll come back to that a bit later. And these things can be trillions of miles in size. I mean, just the scale of these objects is absolutely massive. So we're not talking thermal radiation, something that's just hot and glows. We're talking something where you have particle accelerators. And so down here in this lower corner, what you see is a common plot in our field where you have power versus energy. Okay, and then the lower bound you have, it's basically always has 2 bumps. Okay, in various different flavors. It can have different shapes and sizes. Some are brighter, some are dimmer. Yeah. And what happens is that the lower energies is 1 bump. You have sort of X-rays being created by particles, and these particles get accelerated and they radiate. And then what happens in this higher energy bump is that these high energy particles interact with something and they give off the gamma rays. And that's basically the very short way of explaining gamma ray radiation. So how does gamma ray astronomy work? Well, what you have is up in the sky, you have a source. It gets off a gamma ray, it travels to Earth, it hits the upper atmosphere and creates a particle shower. This particle shower then emits Cherenkov light because these particles are traveling faster than the speed of light in the air. This Cherenkov light then illuminates an area on the ground about 300 meters across. And what you can do is you can stick a telescope on this ground and thereby indirectly detecting the gamma ray. And what's nice about this is called the atmospheric Cherenkov technique, is that if you put 1 telescope anywhere in this light pool, you've effectively created a telescope that's a square kilometer in size. And this is important because the fluxes of gamma rays, meaning how many come per unit area, per unit time, are really small. And so you can't actually fly a satellite big enough to actually do gamma ray astronomy. And this technique was pioneered at the Whipple Observatory on Mount Hopkins. And what's really nice about this is that you can put multiple telescopes within this light pool and you can do this technique much, much better. Okay, so this idea was, started out in the 1960s. And you had a bunch of people using old World War II surplus devices, and they weren't doing gamma ray astronomy at this point in time. They were just, instrumenting radar stations and things like this with mirrors and just trying to detect this light, this Cherenkov light itself. Okay, and one of these famous guys, Neil Porter, was based in Ireland, and he actually trained my predecessor at the Smithsonian, Trevor Weeks, who was really considered the founder of this field. Okay, and a lot of the early, very high energy gamma ray astronomy stuff, really they knew they had no chance. And so, where we tie into Arizona, is when Trevor came out with the Smithsonian with a bunch of World War II searchlights. He parked them out in the desert in Arizona, Coronado National Forest. And you can see this picture right here. He had 2 searchlights, set up a trailer, pulled them off the side of the road. You can see this picture. And they tried to do some very high energy gamma ray astronomy out there. And what's interesting about this photo is not that they had any success out there, but this place where they pulled off the side of the road is actually the base camp of the existing Whipple Observatory. And you can actually see the VERITAS array right there. And if you look real closely at the background, you can actually see that it matches very closely. And so they didn't actually have any success with this device, but what they tried to do was set the foundation for the next thing you see, which is building the Whipple 10-meter telescope. And so they arrived out there in '67, but their real effort was to build this telescope, which was dedicated in 1968. And so this telescope is about 10 meters across, about 30 feet across. It had a very simple camera. It had 1 pixel dedicated to detecting the gamma rays. And it had 1 pixel, another pixel, which was offset in the field of view, offset to the side, which was dedicated to detecting background. And all they did is whenever a pixel detected some light, it would get a count. Okay, and they'd use a stopwatch and count how many counts they'd get into 1 pixel, and they'd count how many background they'd get, and just subtract the 2, and they'd see if they had a signal. Well, needless to say, this didn't actually work very well, and they had no significant detections for 20 years. And so if you think about that, they struggled for 20 years and got nothing. Indeed, the telescope was in some sense shut down by SAO in 1976. It did get restarted in the 1980s, but in general, for 20 years, the entire field was lacking credibility. And so why didn't this work? And the problem with the first generation of instruments was that there was a lot of background. For every gamma ray, there's 10,000 times more background light from things called cosmic rays. And so what they realized was that the light that you see, these Cherenkov light, these showers, they actually form in, an image, if you could, in the telescope that looks like an ellipse. And if you could somehow take a camera and take a picture of this image, you would see an elliptical image for gamma rays, and you'd see a very clustered, ugly looking thing for background. And so the idea was is if you could somehow create a camera to image this light, you could use the shape to project the background. Now, mind you, this is the 1980s. We didn't all have digital cameras. A Polaroid was pretty much the high-tech, cutting-edge technology at that point in time. And so this was a big deal. How do you create a high-resolution camera? And so they got some money together. DOE helped out a little bit, and they put together a 37-pixel camera and installed it in 1983. And they ran this for a while, and you can see what this camera kind of looked like graphically. And they ran this for a while, and they got 100 hours of data between 1985 and 1987, and they detected the Crab Nebula. And you can see what the detection looked like. It's just kind of a plain, boring looking graph, okay? But they knew they were on the right path, and by 1988, they installed a 109-pixel camera, and they detected the Crab in about 25 hours. And then by 2000, they had a 331-pixel camera, and mind you, the electronics are getting better, the computers are getting better, and they were able to detect the Crab in 1 hour. So what took 100 hours in 1985, was down to 1 hour about 15 years later. And by 2000, with all this increase in technology, they had 6 credible sources. Of course, Arizona folks weren't the only people working on this. They were working on this. A German group was working on this in the Canary Islands with a project called HEGRA, which was a system of 4 telescopes, or 5 telescopes, excuse me, but they were smaller, about 4 meters across, maybe 12 feet or so. And there was a project in the Pyrenees run by a French group called CAP, which had a much better camera, a 550-pixel camera. It was about 6 meters across. And the idea with the HEGRA instrument, which was really particularly noteworthy, they put a bunch of these telescopes in this light pool, and they used the average shape of these images and the intersections of the axis that ran through these things to use this information from this to gain more information about the showers and do gamma ray astronomy a bit better. And so all of these different instruments, work together, and they all had about similar sensitivity despite different characteristics, if you will, fundamentally by 2000. But really what they did was they ultimately laid out the path forward where an array of larger telescopes, say on about the size of 12 meters, with high resolution cameras became the clear path forward. And that's where VERITAS came in. VERITAS itself, if you look at it, is 4 12-meter diameter telescopes. They're on a square of about 85 meters side, so about 100 yards. And they have about a 500 pixel camera. The prototype was built in 2003. It began full-scale operations in 2007. And as we heard earlier, it's at the Whipple Observatory in the Santa Rita Mountains. Just looking a little closer at VERITAS, you can see that the telescopes are really big. There's a person right there. The camera's up here. All the signal comes out of the camera down wires and these arms here, and they run to these trailers over here, which have about $1 million worth of electronics to help with the signal processing. Okay, the mirrors themselves are about 2 feet across. They're made out of glass. They have aluminum on the front. The pixels look right here. They're about 1 inch across. Okay, you can actually hold them in your hand. You know, they've got a pretty good heft to them. And you can see the camera itself. This is about 5 foot across right here. So it's a really good size camera. It's a big object. You can see the 500 pixels laid out in a sort of a circular pattern to give you an idea what the hardware looks like. Where does VERITAS fit in the global picture? Well, it's the most sensitive observatory in the world. It detects the crab in about 30 seconds. But there are other facilities. There's HESS in Namibia. There's MAGIC, which is 2 17-meter telescopes in the Canary Islands. And there's another very curious observatory called HAWK down in Mexico, which is a completely different technique, but it complements us. Okay, so what has this new technology done? Well, in 2002, there were less than 10 TeV gamma ray sources. Now they're about 200. So we've seen really explosive growth, and this matches growth you've seen in other fields. In X-ray, there was, they got their first source in 1960, and then it took, 5 or 10 years, they got to 10, and then they got to 100 sources, and then 1,000, and then 1,000,000. And you see this in satellite or lower energy gamma ray astronomy, where they have the same pattern growing. And you can see in TeV gamma ray astronomy, we are also growing. Okay, you can see the distribution of sources. This is what we call a galactic projection, where you see a whole lot of sources along the galactic plane, and then things outside the galaxy out here. The colors themselves denote different flavors of astronomical sources. And so you see that outside the galaxy, there's really one kind of source, and inside the galaxy, there's a whole bunch of different things going on. Okay, so what are we seeing inside the galaxy in general? Well, we're here on the outer edge of the Milky Way, which is a spiral galaxy, and we're looking in, going across. And if you look at the Milky Way in the inner band, you can see it, and this is a plot of what you see at different resolutions. So if you get slightly fuzzier resolution, meaning like, I don't know, if you take off your glasses, it gets a little blurrier, and more blurrier, and very much blurrier. You see that at the finest resolution, you have a lot of point sources, you have some bigger objects, and as it gets blurrier and blurrier and blurrier, it looks like a wide band. And this is actually what they see in satellites, is this wide band. But if you have better and better eyes, if you will, you get to see more and more discrete points. So what are some of these discrete points? Well, some of these things are supernova remnants. They're the death of a star, a massive star. Basically, when it runs out of gas, the radiation pressure stops, and all the matter comes down and collapses, and it bounces off the core. It causes a big explosion that's briefly brighter than the rest of the galaxy. And as it expands, this shell of this explosion expands outward, interacts with matter, creating a shell-type structure. Sometimes it leaves something in the middle, a pulsar or some central object in the center. And a lot of these things are detected up to 100 trillion electron volts. That's an enormous amount of energy. There's dozens of these things out there. So there are things called pulsar wing nebulas. Here, you have an object where there's a pulsar, which is a neutron star. So it's a big collection of neutrons. Probably remember these particles from particle physics that you had in school. And this thing where you have a spoonful of neutrons, weighs far more than a planet, right? And you have this big ball of them, and it's spinning rapidly, and it has this wind shooting out the ends, and it's like a lighthouse, if you will, and it's spinning and spinning, and this wind coming out the ends accelerates electrons inside this nebula, and you see this supernova remnant right here, and as it expands out, it leaves this void behind, and within it, you're accelerating particles. Okay, and these particles then radiate, creating X-rays and optical light and gamma rays. And so sometimes you have a nice circular void, but oftentimes, sometimes you have a higher density area and a lower density area. So the shell of the explosion, it expands asymmetrically, and so you can get some weird shapes of these things. And so this is what one of those things might look like. Some of the other things we see, and so just to give you an idea of what some of the pictures we look like, we get shell-type supernova remnants, and here's just the moon on one of these things for scale. You see a beautiful rim, voids, all kinds of things. That's what a point source would look like. Sometimes you get things that are just weird looking blobs with different pulsars around, but the shapes will change with energy. So if you look at lower energies or higher energies, the shape changes. And all of this, of course, has scientific background that I don't have a lot of time to go into, but we're trying to map these things out, because when you map it versus energy or something like that, you get information into the underlying process. What's really curious about what we are seeing in the galactic plane, and here's some more just pictures to give you an idea of how crazy some of these things look, is that we don't even know what half of these sources are. They're just not seen in other bands. Somebody had the great idea to call them dark sources because it implies dark matter or something like that, but it really isn't that. They're just not seen in other wave bands. And there's actually good physics reasons behind that. But a lot of it is just because the other wave bands haven't had a chance to look yet. Okay, but one of the things that are near and dearest to my heart that we're seeing are things called active galaxies. And what these are, they're found in about 5% of all galaxies are active galaxies. And what they have is a nucleus at the center. All galaxies have a giant black hole at the center, where it's either 1 million or 1 billion times the mass of the sun. And in the active galaxies, you have this behavior where you have a big disk around it, surrounded by a torus. So think like a tire, okay? And onto this black hole, matter is streaming in, and you can imagine there's clouds and all kinds of stuff going on. But in some of these things, there's a jet shooting out of it. And not just a little jet of particles, but like a huge jet. So think of some like cosmic Death Star, if you will, right? Where it's like, zapping some stream out along the magnetic poles, if you will. And this highly relativistic flow of particles, sometimes is pointed at Earth. And in this flow of particles, sometimes you get gamma rays being produced. And so what we see depends on the shape of this jet. Is it super tight, or is it like, bushy, things like that, and how closely it is pointed to Earth. And about 40% of the TeV sources are these, AGN, these active galaxies where the jet is pointed right at us. And so the thing you want to know about AGN is they don't just shine, but they change in brightness by a lot. And so this is a plot I made, or a graph I made in, I think, 2006, when I discovered an extremely variable event that my predecessor, Trevor, was writing to Nature about it, described it as photons from a hotter hell. It was, I think, one of the most iconic images in our field. And what you see here is something called a light curve. It's flux, by how bright something is versus time. It's about a 90-minute episode. This dashed line is the brightest source in the TeV sky, okay? This thing is normally 100 times less bright than you see here, okay? And what it did was it got 100 times brighter than it normally is, and it started varying. Now, mind you, this is an entire galaxy, and it started varying on time scales of a minute, okay? So it's just suddenly, oh, I'm gonna decide to go 100 times brighter and fade away, and then 100 times brighter and fade away. And you can actually use the time scale of these variations to say how big this is. And so it's something about the size of a solar system that is changing the entire brightness of a galaxy, and mind you, this thing is literally, 1 billion light years away. So, it's the scale and the scope of these things is amazing. Okay, so let's go back to VERITAS. What does VERITAS see? Well, we've seen 64 objects. You can see it again projected out onto the galactic sky. The color of the dots are the different flavors, okay? About 2/3 of what we see are extragalactic objects, and 1/3 are galactic objects. We have 8 different flavors of things, and I can't talk about them all today. But there's a lot of interesting stuff going on, so I wanted to share some of my favorite objects. So I'll start in the Milky Way, which you can see up in the sky in this photo of VERITAS. And so one of the things we see is the Tycho supernova remnant. This is remains of a stellar explosion from 1592. So we call this a young supernova remnant. And, maybe when I'm, 400 and something years old, I could view that as young. But what you see is this beautiful image of this, it's a Chandra image, imposed with the Hubble Space Telescope of a Tycho supernova remnant. And our image, sadly isn't quite as beautiful. That's this thing down here in the corner. And you can see the contour image from the upper image down here. And so we just see basically a blob. Okay, all that isn't terribly exciting in some sense, right? And the reason is that our point spread function for gamma rays is large, okay? It's not overly large like the Fermi satellite, but it's large enough that we can't make that pretty picture you see in the upper corner. So why is this image one of my favorites? Well, the reason is what we see in this plot over here, the big one I'm showing. And what you have here is a distribution of power versus energy. And you can see the radio data taken by another observatory, some X-ray data taken by an observatory, data taken by the Fermi satellite, and data taken by the VERITAS satellite. And what all of this combined data does is when you model it, you can say, okay, what created the gamma rays? Could it be things called hadrons? And a hadron is just a proton. You probably remember that from school. Or was it created by electrons? Well, if it was created by electrons in the gamma ray band, you'd have a bump that looks like this kind of sharp rise in it, or a gradual rise and a sharp fall. Or if it was created by protons, it would be flat. Okay. And so because it's more flat like this, or actually declining in descent, you know that it was a proton accelerator. It was the first time we found something like this in the sky. Another object we see is now what we call a middle-aged supernova remnant. Okay, and mind you, middle age means 30,000 years old in astronomy, which seems a bit ridiculous. Okay, and it's IC443. And because it's a bit older, it's had a chance to expand outwards. Okay, we start to see a bit more of a shell type shape. You see where it's been interacting with one of these clouds on the horizon. Okay, and again, you see this flatter shape in this spectral energy distribution on power versus energy. Okay, and again, you see this hadronic acceleration, this proton accelerator. So we're seeing a bunch of these now, and that's really a big deal for the next thing I'm going to show. And that is because it's always rainbows at VERITAS. We always, find great things. Okay, unfortunately, I can tell you, I actually walked into the edge of this rainbow, and there is no pot of gold there. I'm sorry to inform you. But we did find another pot of gold. And that is the origin of cosmic rays. It's been a mystery for a long time. In 1912, Victor Hess, they knew that there was radiation coming down from the heavens, or there's radiation on Earth. And he thought it was actually coming from the ground. And he thought if you went up in his balloon and measured it, it would decrease as you went away. But actually found that it increased if you went up in the sky. And so he called it as cosmic radiation. He got the Nobel Prize for this. But people didn't know where it came from, and its origin 100 and something years later is still a mystery. Many people think it comes from these supernovas, the explosion of massive stars, but we aren't sure. But one way to prove that it comes from supernovas is follows. First, okay, well, how do you do this? Well, if cosmic rays come from supernovas, the way you say is, well, supernovas or supernova remnants would accelerate cosmic rays. Well, the same process that creates cosmic rays must create gamma rays. Okay, you say, well, if you see 1 TeV gamma rays, okay, then if you have 100 TeV cosmic rays have to create those. So if you detect 100 TeV gamma rays from a supernova remnant, okay, well, that's telling you you're accelerating particles in supernova to those energies. Then, and I've mentioned we've seen that dozens of times. Also, if you show that the gamma rays are coming from hadrons, as I just did, well, now you're showing that you're accelerating protons to that energy. So you are accelerating cosmic rays to that energy, supernova remnants. So the last thing you need to do then is that you show that supernova remnants accelerate enough cosmic rays or enough protons to account for them all that we're seeing at Earth. And that's what we tried to do using observations of a starburst galaxy. So starburst galaxies are created when two galaxies interact. And you can see a picture in the upper corner of two galaxies colliding. When they get done colliding, they create something called a star formation region or a starburst galaxy, where right at the center, there's a huge region where lots of stars are being born. Okay, and what happens when lots of stars are being born is eventually lots of stars start dying and they go supernova. And if they go supernova, then you have a lot of, and you believe that supernovas create cosmic rays, then you should have a lot of cosmic rays. Well, the other thing that happens in the starburst galaxy is you have a lot of dense gas in the middle. And also, if you have a lot of cosmic rays and a lot of dense gas, those things are going to interact. And when they interact, the first thing you get is a lot of TeV gamma rays. And so if you believe that, that cosmic rays are created if you believe that, supernovas are the origin of cosmic rays, then you should see starburst galaxies. And so one of the first things we did with VERITAS is look at the iconic starburst galaxy M82, and we looked at it for a long time. Okay, we looked at it for almost 180 hours. He took out all the bad data, and we found 91 gamma rays. It's one gamma ray an hour. It's actually not even. Okay, but we saw it. Okay, and that's a big deal. If you start propagating it through a model, which you see right here, and I won't go into all the details there, you can just kind of trust me that, okay, there's some fancy model and nature was willing to accept it. You can propagate backwards and you find out that the cosmic ray density in M82 is about 500 times that of the Milky Way. Well, that's pretty high. So remember, a lot of cosmic rays, a lot of gas, you get the idea. And if you start working through, the density of these cosmic rays implies that the supernova rate has to be 10 to 30 times higher in M82 in order to support this density. And that is precisely what you observe in other wavebands. And so this may not be exactly the smoking gun, but it is pretty as close as you're going to get to demonstrating the origin of cosmic rays, a 100-year-old mystery. Okay, we see lots of cool things with VERITAS. You spend enough time out there, you take pictures of the moon, Jupiter, Venus with VERITAS. But we want to explain the unknown, not things we know so well. And so you remember I said about half of the sources, in the TeV sky were unknown. And so this object, which is called TeV J2032 plus 4130, was the very first of these unknown objects. It was discovered in 2002, and it has a lot of crazy theories for its origin. Gamma ray burst remnants, dark matter, you name it. Okay. What you see over here in the corner is a result from an observation we made for about 50 hours, the best ever detection of it. Okay, about 5 years ago, give or take. Okay, and it looks like a blob. It's a bit asymmetric. It's elongated. And what you see here are observations made in radio and infrared. Okay, and this tracks molecular clouds. And what you can see here is these are the contours of the VERITAS observations that the VERITAS data fill, or the excess, if you will, the gamma rays, fill right in the void. What you can also see right here is a pulsar. And so if you remember, when I showed earlier about Pulsar Wind Nebula, there had to be a pulsar and there was a void that was swept out by a supernova remnant. Without going through a lot of complicated stuff, I think you can understand that, this has a lot of characteristics of these Pulsar Wind Nebula. And so we went through a lot of rigor to publish an article that showed that this very first unknown object was actually a Pulsar Wind Nebula. And I would say that many of us would bet a lot of money that these unknown objects are Pulsar Wind Nebula. Now, but it's always more complicated than the simplest explanation. And this Pulsar Wind Nebula actually has more going on. It turns out that this pulsar is also in a binary system. And it's in a binary system that has a 50-year orbit. Okay. And this thing came in 2017, it came at its closest approach. It's orbiting a massive star. And in 2017, it came as close as it possibly could to this massive star. And the next time it's going to happen is 2067. I'll be in my 90s. I'm probably not doing too much astronomy at that point, but you never know. And so we decided, let's observe it and see what happens. And what you can see is a plot right here of what happens when you subtract out this blob and what you would normally expect to see and what's left over. And you can see we have a signal. And so what we ended up seeing was that, when we looked at it with the X-ray satellites and with VERITAS, that the X-ray satellites see a varying signal. The gamma ray telescopes see a varying signal. Okay, and so we actually see that the emission from this object varies. So we have a binary system on top of a Pulsar Wind Nebula. And naively, the modelers would expect that the X-ray emission and gamma ray emission track each other, but they don't. And so it's really, complicated what's going on. It doesn't match expectations. And that's why, in some sense, they're unknown objects, because there's a lot going on. We see a lot of binaries. What you see here is a plot called a light curve versus phase, where you have a binary period and you say, okay, it's going to come around every 300 days. What does it look like the 0th day, the first day, the second day, the third day, the fourth day? And that's what this plot is. And you can see when you get structures, it rises, it falls, it rises, it falls. And so we observed another one of these unknown objects, and we saw this periodic behavior and established that it was a binary. And so, a lot of these objects, there's about 100 of them, are unknown, and you just have to look at them deeper with better instruments, and VERITAS is the best in the world, but, it takes us, 200 hours of data to establish this one. So there's a lot of work to be done. Okay, you might have gotten the idea that, listening to this unusual scientist speak about an unusual telescope, but VERITAS is very unusual and we see unusual things. Okay, well, the Crab Nebula is not so unusual. It's beautiful. You see this image of a remnant itself. It has a pulsar at the center from this Chandra image. And this crab is astronomy's most well-studied object. It's also the brightest steady TeV gamma ray source in the standard reference for a field. Well, VERITAS detects it in 30 seconds. So you wouldn't think we'd see something unusual from it. Well, turns out you're wrong. Okay, and that is that the gamma ray flux from VERITAS actually varies periodically. Well, it's not surprising. There's a pulsar in the crab. Okay, it varies at a frequency of about 30 hertz. Okay, and so what you can do is you can take out the steady emission from it and start looking at what's on top of it. And you see that it has this structured behavior that repeats, every 33 milliseconds, a bump, a bump, a bump, a bump. And so it's not surprising that there's pulsed emission there because you see it in the radio band, you see it in the optical band, and you actually see it at lower energy gamma rays. But all of the best theorists in the world would have bet, I don't know if they'd bet all of the money they had, but a lot of it, that this thing would have cut off as you get the higher and higher energies. The spectrum, if you will, the amount of power would have gone down following this dashed line. But it turned out when we saw this in 2011, we see it out at 1 trillion volts at 1 TeV. And that came as a shock. It broke almost half of the models. In fact, I don't even think they had a single model that could explain this. And now they're finding more and more of these that are doing that. And of course, the crab, you think, okay, well, that's surprising. But remember when I said the crab was a steady source? Well, it turned out that the Fermi satellite, which was lower energy gamma rays, actually started seeing bursts of gamma ray emission from the crab. So this is the light curve of flux versus time. And you can see this, 20 times brighter and then goes away again. Well, VERITAS, happened to be observing at the same time as Fermi, and we didn't actually see this. So why is it when you're looking at, say, 1 billion volts, it varying like crazy, but it's not varying at 1 trillion volts? Naively, you would think they do the same thing, and we're not seeing this. So the crab is full of surprises, and that was a real shock as well. Okay, VERITAS is also pretty inspirational. I mean, I think, finding a new field of astronomy is great stuff, but, we're doing some really, artistic things as well with the project. And so what do I mean by that? Well, you may recall I showed this plot earlier. Well, what this is power versus energy, and these are for AGN. And so there are different kinds of AGN, some that peak at lower energy, and this is the same thing, and some that peak at high energies. And when I first started in this business in the mid-90s, we used to only see this one flavor called high frequency peak BL-lac objects. They're not as bright, but this higher energy peak reaches out into the TeV band where we see things. So one of the first things we did in VERITAS was try to catch this other type of AGN, lower peaked objects, flat spectrum radio quasars. There's far more of these in the sky they generally don't see. And we actually ended up discovering the first 5 of these at TeV energies. We also found flat spectrum radio quasars and radio galaxies, where we're not now looking down the Death Star or the barrel of the jets from these AGNs, but we're actually looking at it off axis, which allows you to probe the structure. Now, okay, it may not have been an enormous surprise that you see these, because remember I told you these things vary and sometimes they get 100 times brighter. And so the first one we saw, what you see right here, was actually one of those cases. You see its light curve. So this is the flux. It's basically 0, 0, 0, and then all of a sudden it spikes and then it goes away. And you can see a zoom, and okay, that's when we caught it. But we actually now see low states. It takes us about 50 or 100 hours to see it when it's not so bright, but we do pick it up. But what this upper plot shows, which I find is interesting, is it shows that it's giving off X-rays, and we saw it, and it didn't do anything crazy in X-rays, and then like a month later, it did something super wild in X-rays. And of course, we weren't looking at it when it did. So it's kind of telling you that these things are kind of going up and down, and maybe you catch it, maybe you don't. And ideally, you'd like to be looking all the time. It's hard. So it's a very tricky business catching these things. But how is this inspiring? Well, when I showed one of my friends who helps run a museum out in Tucson at the Arizona State Museum this thing, it turned out that when we discovered this thing, it actually was the second object in the same field of view. So he asked me to put on an art exhibit about this, and it got on display at the Arizona State Museum. Okay, and that was a pretty big deal. 2 point sources in a single field of view for one of our telescopes. Mind you, we didn't see anything for 20 years. Well, in 2011, it turned out that we got a third object in that same field of view. So that was great. So a little premature with my museum display. Well, now we are here 2015, 4 years later, it turns out that we now have 6 objects that fit into this field of view. So if you think about that, and now we're making constellations, maybe we have a little too much time on our hands or something like that, but it's a lot of fun being able to make constellations. And I think you now realize that the period of real astronomy with VERITAS has arrived. We're making constellations with TeV sources. And all of the different flavors of AGN are represented in this image we call the Tera-bird. And of course, it's half in jest, but a lot of fun all the same. And of course, we're not just stamp collecting. We can model these objects. You see power versus energy here, and you have optical data, X-ray data, Fermi satellites. This is lower energy gamma rays. This is the VERITAS data over here. And what I want to show you, this is not explaining the model, but when you model these things, you see the curve right here. You drive the best line, which is this black line through it, and fit to the data. Now, if you change the parameters, say the magnetic field or how massive the object is or something like that, you'll get a slightly different result. And the dirty secret, I think, in a lot of astronomy is that you can tweak these numbers just a little bit and you get more or less a comparably good, model to it. So, okay, that's a little bit more massive. But now the data are so good, but not only can we say if a type of model works, we can say for what range of parameters it works. And that's what this gray shaded area is. And it turns out that we're modeling these objects based on the quality of our data. Mine is the only data you have up here. It's so good. You can fit the data and give parameters like how massive it is or how big the magnetic field is to within a factor of 2. Now, a factor of 2 is pretty terrible when you're building bridges, but when you're doing astrophysics, that's amazing. And that's why, VERITAS is so inspirational in terms of what we're putting out. Okay, well, VERITAS is also a lot of fun. If you stand at 2 focal lengths away from the mirror and the telescope, you can get your head the size of the entire dish. And you can just have a lot of fun just kind of playing around. But you can have a lot of fun doing science. And one of the most fun things I thought I would ever try to do with VERITAS was detect a quasar at redshift 1. Well, what is redshift 1? Well, redshift 1 is 7.5 billion light years away. Now, that probably doesn't mean a whole lot. It's like some incomprehensible number, but you have to remember the universe is about 14 billion years old. So for that quasar, that's halfway across the known universe, okay? Okay, well, it's really hard to do this. Outside of having to be powerful enough, what happens is as gamma rays are trucking across the universe to us, they're interacting with photons along the way. Just light given off by galaxies and stars, optical photons, nothing fancy. But these gamma ray photons interact with them and it creates a positron and electron. It just goes away. And depending on how much light there is, this bright signal you see right here will start to disappear. It could be a lot of absorption or a little bit of absorption, but it goes away. And in 2014, I think it was, and published in 2015. In 2014, my friend Daniel called me from Tokyo and he was very, very excited. It was the middle of the night. And he's like, Wystan, there's something going on this object, Parks 1441. You have to look. I was like, okay. So I called down to the observatory, told the operator to go turn the telescope. And sure enough, we saw it. Okay, and what you see here is power versus energy. This is the gamma ray data. And you see the Fermi signal right there. And this is what we saw with VERITAS. And it turns out that we saw it. It was great during this flare. And, and I would have never guessed we could have seen this thing. Never in a million years. But we ended up seeing it. And it turned out it wasn't actually even a surprise that we saw it. It was so bright. Okay. And so if you take some baseline model and correct it out, you can actually see that correcting it out would just smoothly connected to the satellite. So it wasn't a surprise. But what you can actually do is say, hey, now that we saw it, how much light could there have been? How much of this background light is there out there? How much light was emitted by galaxies and stars all through the history of the universe? How much light could there possibly have been in the way? Effectively, how foggy are my glasses in between me and in this quasar. And that's what you see right here, this blue line. That's how much light there could have possibly been for us to have seen it. Well, what you see right here in these lower arrows is actually derived from just counting the number of galaxies seen in the various telescopes, satellites, Spitzer or things like this. And you can see that the upper bound equals the lower bound. So it basically means there isn't anything mysterious going on. And you can see that here where we did the same study using 14 different blazars. And this blue band right here is the range which is allowed, and this red band bumps are what's the lower number. And you can see right away that, I mean, it's complicated and I know I'm going fast, but the lower bound and the upper bound meet. And so that tells you that all of the light that's in there, this diffuse light permeating throughout the universe is coming from things that you see. It means there's nothing fancy going on. There's no exotic stuff in the early universe that created it. The dark matter hasn't done anything wild. And it has a lot of information for cosmology because this extragalactic background is the integrated history of light emitted across the universe throughout all time. And it's a very important number for cosmologists. And we basically say that, well, what you see is what you've got, and that's what it's always been. So VERITAS isn't complete. We see lots of flares. You remember this big flare I showed you with Parkes 2155? Well, we have a big flare. It's actually the brightest flare ever. It's not quite as fast. We only have 20-minute time scale, but I just wanted to show that we've got one too. But sometimes it's not how big and fast they are that's important, but what you can do with the flare that's important. And so one time in 2011, we saw a flare. It was right before sunrise, and we can't obviously run when the sun is up because if you catch the sun with our telescope, it'll vaporize $1 million worth of electronics. But right before the sun came up, we caught a flare of this thing called BL LAC, and it reached one time as a crab. Normally, we don't ever see this. These are these lower arrows are for it. We've looked and haven't seen it. One time, it was the brightest object in the sky, and then it quickly faded away on a 13-minute time scale. And so, what made this thing go so bright? Well, we tried to explore that. And we called up my friends at the Radio Observatory, and they started looking at it with the VLBA. And what they saw was months later, after we saw this flare, that a new feature right on the edge of this black hole was born. It's called a knot. Okay. All right. Well, it looks like, whatever created this flare was tied into the birth of a knot right on the edge of the black hole, sort of a new structure, if you will, inside the jet of the AGN. Well, we saw another flare in 2016, and again, you see it, another knot was born. Okay, well, that's very exciting. So we've seen this, and we've seen this countless times now. So it looks like what's creating the flares in these AGNs are the birth of knots. Well, many of you may have seen in the news M87 and this thing from the Event Horizon Telescope of the rim of a black hole. Well, in M87, we've also seen this thing where you've had now a flare in gamma rays accompanied with a rise in the radio emission. And we've seen flares now on sub-day scales from this object. And so we are running campaigns with the Event Horizon Telescope. So if we see a flare from M87, maybe the Event Horizon Telescope, which can actually resolve and make a pretty picture right on the rim of that black hole, we might actually be able to catch that happening and image it. Our next campaign actually happens this month, so that'll be very exciting. Okay, so VERITAS is getting a little long in the tooth. We're now 14 years into our mission. We're supposed to go 10, so we're in the extended phase. So what are we doing at sunset? Well, some of the things that we're doing in the sunset days of VERITAS is we're helping out with the birth of neutrino astronomy. Back in, I think it was 2017, this experiment called IceCube, it's a string of photosensors buried deep in the Antarctic ice, discovered 290 trillion volt neutrino moving through the ice, and it interacted and set off these sensors. And they set us an alert saying, hey, we see this thing, we know it's coming from outer space. What's it doing? Where did it come from? And well, so Fermi, Magic, and VERITAS all looked at our data. This is the region of the sky that IceCube set it from, and said, hey, we happen to notice that there's a flaring AGN. Okay, wow. The odds of that happening are pretty small, about 1 in 1,000. Okay, and you can actually see that VERITAS, we actually noticed that it was flaring about a month afterwards. And so it turns out if you start doing all the statistical studies and removing all the probabilities, it's about a 1 in 1,000 chance. Okay, so it's maybe not set in stone, but if this is actually true, it means that this blazar is a source of ultra high energy cosmic rays. And so what we're trying to do is find more of these things. Because if you have more of these cases, you've now proven it, you can do neutrino astronomy, giving birth to a new field of astronomy. And so kind of carrying the legacy forward to the next world. What are some of the other things we've done? Well, we do optical astronomy with VERITAS. Remind you, we're a gamma ray observatory. And so some of the things that we try to do is we try to measure stellar diameters at the smallest scales possible. We call it sub-milli arc seconds. And I don't know if that means a whole lot to people, but what we're trying to do is effectively, you know, it's not so much like measuring the diameter of a quarter on the moon. We're trying to tell you whether you're measuring whether it's a dime or a nickel or a quarter on the moon, if you will. So we're trying to measure the size of stars, and you can do this in a variety of ways. You can do it when you measure an asteroid going across a star, and that's what this plot you see right here. It leaves fringes in the light curves you see. Or you can do something called intensity interferometry, which is something that they used to do in the 1970s. They path-found it, but you couldn't do it. We decided to start doing this again in 50 years. We had a major breakthrough which we published in Nature just last year. And so we have a few press releases. I don't have a whole lot of time, but we're actually starting to pathfind like new technologies for optical astronomy to make catalogs for diameters of stars. Okay, so how is VERITAS doing? Well, I think we all know it was a really terrible year in terms of the world this past year, and VERITAS had to shut down actually on St. Patrick's Day last year. So how did we get through? How are things going this past year? Well, VERITAS switched to completely remote operations over the past year. It used to be we had to have 4 people sitting in the control room operating this complex observatory, and they had to be scientists. And in the past year, we've evolved to the point where we now have 1 technician who turns things on and sits there in case something goes wrong. And we're able to operate with remote scientists. Somebody could be in Berlin, somebody could be in Dublin, driving around these 50-ton telescopes, taking care of things. And through this evolution, which is a lot of work, we've managed to operate through the COVID, this COVID experience, if you will. And as of this morning, we had about 700 hours of data. And so we have managed to get through this horrible time without really missing a beat. I think we want to leave that positive note in people's mind. Okay, so I wanted to mention about the future of where things are going. We've had a lot of success with VERITAS. Well, what is the future? Well, the future is the Cherenkov telescope array. And the idea of CTA, which you see in this picture here, which has a bunch of different telescopes of small, medium, and large sizes, is to enable gamma ray astronomy to go to the era of 1,000 sources and do population-based astronomy. And what is population-based astronomy? Well, if you looked at me and tried to describe mankind or humankind based on observations of me, you'd probably come up with some pretty weird conclusions. So you want to look at a group of people if you want to start describing people in general, okay, rather than just one thing overall. And the more people you look at, the better your conclusions will be. And so the way you do this to get 1,000 sources, you have to improve the sensitivity, and you have to, improve basically how well you're looking at things, how well you resolve things. And so CTA is going to do this by reducing the time to detect sources by a factor of 100 and get astronomy images with 10 times more pixels. And what does 10 times more pixels mean? Well, think of it as going from standard definition TV to your 4K TV that you have in your living room right now. Going from super blurry, like I can't follow the hockey puck, to amazing stuff. Okay. So early construction of CTA began in 2020, so just last year, and we hope to have it implemented by mid-decade, but we don't have enough money yet to finish this thing off. So I don't know when it's going to be finished. It's a big project, 1,500 scientists, 200 institutes, 30 countries, $600 million. It's a big deal. It's going to be located on 2 sites, one in La Palma in the Canary Islands, one down in Chile. And we have a bunch of different sizes of telescopes. We have big telescopes in the middle that focus on the low energy. We have mid-sized telescopes, mid-size meaning 12 meters or 40 feet across. And they focus on the bread and butter, sort of a VERITAS energy range. Then we have small telescopes that do the things up at 100 TeV or 100 trillion volts. And those are spread out over a large area. And you'll notice the little telescopes aren't in the north because the little telescopes help us do galactic science, whereas the big telescopes help us do extragalactic science. So you can do both in the north and the south. Okay, and they're spread out over a very large area. Okay, I can't talk about all the science we want to do with CTA, but if you want to look more into it, please go to our website at ctaobservatory.org. In our science case, we have an open access book. But what you can see right away is we've done a lot of simulations. The northern and southern side are very much equivalent at lower energy, but the sensitivity is very different at high energy. But we are a lot better than the existing stuff, which you see right here. Okay, some of the things we want to do, and I'm starting to run a little long, is we want to look at the Galactic Plane survey. You can see what Hess is seen up in the top. And the field of view of Hess is about 5 degrees or 10 moon diameters. CTA is going to have an 8-degree field of view, so a little bit bigger. And you can see right away that you get a lot more sources to pop out, okay? And so the CTA will look at this galactic plane. It'll survey it 300 times faster. It'll do it 10 times deeper. So you're going to get a lot more and better resolved sources. And so this plot right here gives you the limiting sensitivity, if you will. And I know that probably doesn't mean a lot to a non-expert, but the main thing I'll say is that the dimmest source that we've detected right now is 3 millicrab, okay? That's the faintest thing we've ever seen. The limiting sensitivity across the entire galactic plane is going to be 3 millicrab. So we're going to look at the whole plane of the galaxy with better resolution than the faintest thing we've ever seen to date. And we're going to do this with improved resolution. So you see the supernova remnant 1006 right here. Okay, and you see it has kind of this faint structure and a limb. Okay, this is a Chandra image. This is what it looks like right now, very blurry. Okay, with CTA, you're going to start to be able to resolve these features. Again, you're going from standard definition to kind of 4K TV, if you will, on this thing. Big leap. And why does that matter? Well, of course, it's cool. But the reason it makes a difference is you look at the supernova remnant in Hess, and you see a nice shell-looking thing, kind of a little blobby. But you can actually, with CTA, what you'll be able to do is rather than having to do fancy modeling and projections versus energy to figure out whether it's protons, mind you, this has implications for cosmic rays, or electrons creating the image, you'll actually just be able to simply look at the image, use your own eyes and your own brain to tell you if it's leptons or electrons, which is this left-hand image, or protons in the right-hand image. And it just makes a whole suite of physics possible. You'll be able to do temporal studies better. This is that famous light curve I showed you with the 1-minute variations from the galaxy. With CTA, you'll be able to do 1-second variations. And it's just, again, enables everything to change. So how are we going to do things in the US for CTA? Well, we wanted to change things a lot with CTA in the US. We didn't want to just say, throw money at the problem and do more of the same. And so in 2005, we started thinking, how can we change gamma ray astronomy? And so the way we decided to try to do it was, well, hey, a lot of telescopes have 2 mirrors. Why not try that for gamma ray astronomy? Instead of 1 single mirror surface, go to 2 mirror surfaces. And so we came up with an idea to do this. It's called a Schwarzschild-Couder Telescope. The original design for this came back in 1905, but it was so expensive to fabricate, so complicated, so impossible that nobody tried it for more than 100 years. Okay, but we decided to go for it. And why is this good? Well, what it does is it allows you to make a picture over a very large field of view, 8 degrees. So that's 16 moon diameters, and it's going in all directions now. And what it does is it allows you to have a uniform response over this thing. Big problem in astronomy is if you start making a big field of view, it gets blurry, if you will, on the edges. And so this fixes that problem, but it's obviously complicated. The other thing it does is it allows you to shrink the camera down. So right now, the cameras are about the size of a car or a small car, if you will. And now you start to shrink the camera down to something that, you can't carry it. It's still heavy, but it's, it's about 1.5 feet across. Okay, and this allows you to have better pixels, better photosynthesis. And so we've got a prototype to build this. You can see in 2012, we had the design, and in 2019, we inaugurated it. Okay, and why do you do this? Well, you just get better images of your gamma ray showers, which allows you to separate the signal from the background much better. And if you build CTA with this, it'll require 2 times less observing time. Now, if you think about that, you're building a $500 million instrument and it requires half as much time to use it. I think that's pretty good. Okay, so how does this prototype that we built do? Well, what you see here on the left-hand image is the image of a star. and all of the light falls inside 1 pixel. Okay, it meets design specifications. This is the point spread function, meaning the width of this. It falls on the line. We ideally wanted it to be between purple and red, and at least on axis, it's right here. We're going to make the measurements to make sure that it's all the way across, following at least this green line. And we're going to try to push it down further. It should be straightforward. We haven't aligned it fully yet, but we're there. And early last year, we actually observed the Crab Nebula with it. And mind you, we still are shaking things out, right? It's a prototype, but we actually managed to detect the crab. And so we actually show that this thing works. Okay, we've retired all the technical risks and we're ready to go. So where are we going to go? Well, we're going to finish kitting this thing out. We're going to implement all 11,000 pixels now. Mind you, remember we started out with 1 and now we're up to 11,000. Okay, we're going to improve the electronics. We're going to finish that in the next year. But moving forward, where are we going to go? And well, we're going to find out in a few months the results of something called the Decadal Survey. Every 10 years, NASA, DOE, and NSF get together and decide the plan. And we've asked them to help support about $100 million worth of funding to support our participation in CTA, which is a $600 million project. As I'm running short on time, I'll take questions on this so I can finish up. But I just wanted to say that in summary, the first generation of TeV telescopes was started in 1968 out of the Whipple Observatory and started a new field of astronomy. The first galactic and extragalactic detections were at the Whipple Observatory. And now a third generation of instruments such as VERITAS really established this field as mainstream. We have 200 sources now, and VERITAS is running strong. We have money to go till 2022 and hope to go till about 2025. And the next generation of observatory is CTA, and it's going to hopefully start the era of 1,000 sources. And the US is planning to contribute a dual mirror telescope to it. And I think I'll thank you for your time at that.
All right, thank you, Doctor, for your interesting presentation and taking the time to share with us today what's happening right in the backyard of the Whipple Observatory. I had an early question. I think that you got it answered, but I think we'll go ahead and ask it. Can you tell from your data what is produced by thermal radiation and non-thermal radiation? And does any particular non-thermal radiation dominate?
Well, I mean, our data really literally only shows thermal radiation. So, so if we see something, we know it's at 1 trillion volts. So we're talking literally 1 billion times more energetic than any photon that comes out of any kind of plausible thermal process. Now, what can happen, of course, is that X-rays or particles that are accelerated could actually interact with thermal photons, but these actually destroy the signal that we see. So we're not only non-thermal, but we actually hate thermal photons, if you will. They just don't get along well with us. So we know we're not dealing with the thermal stuff, and so we stay away from stars. Whenever we have something that's radiating thermal energy, it tends to interfere with the things we do and block things. And in some sense, when we start interpreting our data, we know that it's coming away from regions that give off thermal energy.
Okay, well, actually, that looks like that's the only question we had. I hope everybody enjoyed what we saw out there and find out about the significant research that's going on right in our backyard. And thanks again. A lot of comments coming in on what a good presentation it was. So looks like you did a great job.
Well, thank you. And I hope everybody stays safe out there and enjoys their St. Patrick's Day.
I hope everybody can join us again in 2 weeks, March 31st at 10 a.m. Mountain Standard Time or 1 p.m. Eastern Daylight Savings Time. Our guest then will be Dr. Tony Stark, Senior Astronomer for the Center of Astrophysics, Harvard and Smithsonian at the South Pole Telescope. Dr. Stark will speak on the role of the South Pole Telescope in current and future cosmology projects. So join us in 2 weeks and we'll take a virtual trip to the South Pole to see what a telescope there is able to see. So hope to see you then. Amy.
Well, thank you so much, Stephen. And just right after you said that, we got one last question. So listeners, you're still hanging out here. We may have already discussed this question, but we had some people tune in a little bit late. So what expectations can the new telescope provide of black holes?
Well, I mean, that could go a variety of directions, so I'll try my best. So I mean, the main thing is that we're trying to figure out what's going on say the external regions of black holes, like how matter is falling in, how it launches, say, jets, these large scale structures that are, say, 1 trillion miles long, how they interact with the environments around black holes, whether black holes are orbiting another black hole or objects that are orbiting black holes, how those things interact. So we're not going to necessarily discover a black hole. I think it's pretty clear where they are, but the environments around them, we're going to understand them significantly better, and what they might tell us.
Great. Thank you so much, Wystan, for taking that last question. And everyone, like Stephen said, thank you so much for joining us for the 51st annual New Vistas in Astronomy lecture series. And we'll see you again next time. If you have additional questions, you can always feel free to continue putting them in the chat on YouTube. So you can head over to our YouTube channel and continue to ask questions there. Or you can email us at the observatory at whipplesciencecenter@gmail.com, and we will get those questions to Dr. Benbow and get them answered. Thank you again for joining us. We'll see you again soon. Bye.